Hi, welcome. My name is Sarah. I'm your moderator for this afternoon. I would like to introduce the speaker for today. Her name is Syneva Runyan. And when you're ready, Syneva.
Hey, nice to present to you guys virtually. Welcome to my talk in the danger zone, cross-site scripting, vulnerabilities in React. Like Sarah said, my name is Syneva Runyan. I currently work remotely from a small town in North Alaska called Kotzebue, way up here. And I'm an engineering manager at Providence Healthcare Systems Digital Innovation Group. I'm also a recent grad student from Georgia Tech's Online Masters in Computer Science program. And I was actually in that program, I was taking an info security class, and I realized while I could recite the definition for cross-site scripting or cross-site request forgery, I really couldn't picture in my head what the execution of those attacks would look like. And that's what inspired my presentation today. Quick disclaimer before we get into the content. This presentation is solely for educational purposes. I'm not responsible in the event of any criminal charges brought against any individuals misusing the information in the presentation. Break the law. When in doubt, don't do it. Got it? All right, thanks. The problem space. I'll make the assumption here that most of you are familiar with cyber attacks in general. They've become increasingly prevalent in the last 2 years, most recently making headlines with the Russia-Ukraine war. It was predicted that by the end of 2021, the annual cost of cybercrime damages was expected to meet $6 trillion. If you break down that statistic, the mean cost of a single digital incident is $200,000. Now, if you're a small business, $200,000 is a lot of money, and 43% of attacks were aimed at small businesses. Of those small businesses attacked, 60% of those businesses went out of business within 6 months of the digital incident. So $200,000, a lot of money for a small company, but let's say you work for a big company. Proportionally, $2,000, maybe you're thinking that's not that much money. But it turns out that larger companies do experience larger losses. You'll see in this infographic that there are numbers like $78 million, $26 million, $42 million. And the larger company you are, the more likely you are to experience a cyber attack. So you can see among the top 250 Fortune 1000 firms, there's a 45.5% likelihood that you'll experience a digital incident in a given year. Going back to that $200,000 number, the mean cost of a digital incident is $200,000, but there's a 10% chance it could be 100 times that or higher. So whether you work for a small company or a large company, how can we as developers work to combat cybercrime? In my opinion, some of the best things we can do are educate ourselves on vulnerabilities and incorporate mitigation practices in our day-to-day workflow. Now, it's worth mentioning, I'm about to talk specifically about cross-site scripting attacks, but there are literally hundreds of thousands of web security vulnerabilities that exist out there. So if you're interested in the topic, I'd really encourage you to go and do your own research after the presentation. But in the meantime, cross-site scripting attacks. So by definition, a cross-site scripting attack happens when malicious code is injected into a web page and executed in the browser. So an example flow of this attack might look like here. There's an attacker here, let's say they write a malicious script and inject it into the web page. They then need to get the victim to open that web page. So they might send a script injected link to the victim. The victim might then click on the link, and in their browser, a legitimate website will load. But right next to that legitimate website, the attacker's malicious script opens as well. When that script opens, it might do things like send the victim's personal information back to the attacker. So you have a flow there. A famous example of a cross-site scripting attack happened in 2014. It was targeted at eBay. So the attackers posted listings for really cheap iPhones. When someone went to click on those really cheap iPhones though, it actually prompted them to enter a password. They'd enter their password and be redirected to a page, but when they had entered that password, those passwords were actually sent back to the attacker, and the attackers then compromised their accounts. Similarly, In 2017, there was a cross-site scripting attack aimed at Steam. In this case, the attackers created some malicious profiles. When users visited those malicious profiles, malware would actually be downloaded onto their computer, and they'd again be prompted to enter their credentials into a fake input form. When they enter their credentials, though, those credentials were sent back to the attacker, and then in the background, the attackers would use those credentials to silently drain the innocent victims' Steam wallet funds. So now that we've talked about cross-site scripting attacks in general, let's take a deeper look specifically at the React API and understand maybe what it does to help us as developers mitigate cyber attacks and maybe what it doesn't do as well. In order to demonstrate that, I'm going to show some cross-site scripting attempts. Each of these are crafted with the goal of stealing social media profile passwords. I'm not actually going to show you how to steal social media passwords, so I've created this lovely fake website to go through in these examples. So you can see in this fake social media website, there's a functionality of viewing people's profiles here. You can see each person's profile has a name right here. There's links to various social media accounts as well, images, and then a rich text bio. Using the site, you can edit your own profile information, uploading a picture, changing your name, changing the links, etc. And then, importantly, to this cross-site scripting attack, there's a session timeout that users are used to seeing if they just leave the website open on their computer for too long. They're going to be prompted to re-enter their password. So, taking on the persona of an attacker, I understand that users might be used to seeing this page and might be used to just entering their password whenever it comes up. So I think I might be able to create a fake version of this page when somebody's browsing the website. But instead of like this fake version of the website, instead of like just relogging the user back into the page, when someone submits this fake version of the session timeout screen, I want their password to be sent to me, the attacker. All right, so I have this idea of a script in my head. So let's see if we can get it loaded onto the web page. In this first attempt, I want to try to load that malicious script and save it as a user's profile name. When the profile is loaded, I want my script to be executed instead of displaying a user's name. So if my attack is successful, when somebody views the malicious profile I've created, they're going to see this fake timeout. This is something like what the script would look like. You can see I'm using the script tags here. There's an auto executing function. I'm creating some elements and appending it to the DOM. Here's being prompted that their session's timing out. They'll be prompted to re-enter their password. And then most importantly, I have this fake on submit. When a user submits their form to my fake form, submits their password to my fake form, it's going to be emailed back to me, the attacker. All right. So let's take a look and see what the attacker is going to be doing. Here I am looking at the fake social media page. I go to edit my profile. And here, instead of my name, I'm going to paste that script right there with the auto executing function. And then I'm going to go ahead and save these changes. All right, so I've created this malicious profile. Now I just need to get users to visit the profile page. In order to do that, I might craft a phishing campaign. So I might send a simple email to users that looks something like this. Hey, do you know Kenny Loggins? If so, check out his profile. When a user clicks on this link, I want them to be redirected to that malicious profile page. I want my script to be loaded and executed. Jumping into the persona of the innocent victim. So you're checking your email. Hey, do you know Kenny Loggins? Let me check out his profile. So I click and look at that. Okay, so clearly something's not working. You can see this awful script here, but I'm not being fake timed out and I'm not seeing that prompt to enter my password. So in this case, it turns out that React is actually preventing a cross-site scripting attack from happening. So my script was printed out as a string on the page instead of executed. Let's take a look at the JSX and kind of understand how React was able to do that and what's going on. So this is an example of what the JSX might look like. You can see there's an H1 and there's the profile name here. So behind the scenes, in order to get this JSX to load on the page, React goes through a process called transpilation. So in that transpilation process, this JSX is transpiled to basic JavaScript, and the React API is used in order to append elements into the DOM. Of particular interest to us in this example is the use of the create element API. So the create element API takes in a type, it takes in props, and it takes in children. In our example, the type right here, H1, there are no properties here. And then the profile.name, the malicious script that means the attacker put together, is passed as this third parameter right here as the child. The fact that it's the third parameter is important because behind the scenes, React will review data passed here and auto escape scripts for you, successfully preventing the first attempt at a cross-site scripting attack. That's why you saw, again, this ugly string right here. All right, well, I'm a persistent hacker though, so my first attempt didn't work, but let's try another attempt. In this case, I want to try to save my script maybe as the profile YouTube channel right here. If my attack is successful, again, the user will be shown this faked timeout screen, they'll be prompted to re-enter their password. If they re-enter their password, that password is going to be sent back to me, the attacker. I've modified the script a little bit in this case as well. So instead of using just the script tags, I've now taken advantage of the JavaScript protocol right here. You might be familiar with the HTTPS protocol, the mail-to protocol, the tell protocol. In this case, the JavaScript protocol probably does exactly what you think it does. It'll execute the script provided to it. All right, so let's see what we're doing in this case. You can see I'm back to the edit profile page. I'm going to the YouTube channel right there, and then I'm pasting that script to the JavaScript protocol. I'll go ahead and save those changes. Rather than crafting a whole phishing campaign in this case, I might just say, hey, I'm going to rely on people visiting Kenny Danger Zone Login's profile page. So, persona of the innocent victim, hey, look at that. Let me check out this profile. They might click on the profile. They might be interested in Kenny Loggins' music, so we click on the YouTube link there. And look at that. As soon as they clicked on the YouTube link, we saw the fake timeout pop up. Let's play that again really quickly. So click on the YouTube link, fake timeout popped up immediately. So that is actually the malicious script that I wrote being executed on the screen. They enter their password. That password is sent back to me, the attacker. All right. So we've seen a successful attempt at a cross-site scripting attack. So why was this one successful when the first one wasn't? Let's take a look back at the JSX to understand a little bit why. You might already notice a difference here. So in the first case, the profile name was passed as a child to the H1 element. In this case, the href is used right there, and you can see the profile.youtube channel there. That property, the href, is passed as the second parameter to the create element function. Behind the scenes, props don't have the same built-in cross-site scripting protections as children. ***. Why is there a *** there? Well, it turns out, so my fake social media page is built with React version 17, but in React version 18, the React team has actually realized that the JavaScript protocol right here can be used to successfully create cross-site scripting attacks. So in future versions of React, this exact type of cross-site scripting attack will be prevented. It's just kind of cool. But for now, while most of the world is still using React version 17, this is a legitimate vulnerability that exists. So how can we as developers prevent this vulnerability? Well, we can integrate these mitigation practices into our workflow. So first off, we can validate any protocol that a user may provide to us. So you can see right here, if we're expecting a URL, let's go ahead and make sure it's an HTTPS URL. We can also validate the expected value. I specifically asked for a YouTube link, so let's check and make sure the user actually gave us a YouTube link right here. We can practice defense in depth, so we can practice validating the URL before it's saved and sent to the server. We can again validate when the URL is sent to the server before it's saved in some sort of persistence layer. And then if we want, we can actually validate the URL before displaying it on the page itself. In summary, don't trust, always verify user input. All right, so that second attempt, it was successful for now, but once the world moves to React 18, I don't want to have to rebuild a cross-site scripting attack. I want to do one solution and have it work forever. So let me try this third attempt. In this third attempt, I'm going to save a version of the script as the profile's bio here. Again, if this is a successful attack, when my script is executed, I want the user to be shown this fake timeout screen. I want them to be prompted to re-enter their password. I want them to re-enter their password, and I want that password sent back to me, the attacker. Again, I've modified the script a little bit. So in this case, I'm adding a button here with an on-click event. And then underneath, I have this lovely picture of Kenny Loggins. When that image is loaded, I want that button to be clicked, and I want this function to be executed. Jumping back to the hacker persona, you can see I'm editing the profile page again. I go and I paste my script as the bio down there. You can see the button with the on-click event. And I'll go ahead and save those changes to my profile. So I again have created this malicious profile page. Jumping into the innocent victim persona. I'm just browsing the site. I see Kenny Danger Zone Logins profile. So let me go ahead and click on that profile. And immediately this time, you'll see that the malicious script has loaded and the user was fake timed out, prompted to re-enter their password. They're re-entering their password there. When they submit it, it'll be sent back to me, the attacker. So this is another example of a successful cross-site scripting attack. So let's see if we can understand again why exactly this was a successful attack. The first thing you may notice when looking at this JSX is the use of the dangerously set inner HTML prop right here. So when you see the word dangerous, I want you to hear this music in your head. Yeah, so React did not accidentally name this property dangerously set inner HTML. Dangerously set inner HTML does not have built-in cross-site scripting protections, as you may imagine. So that's something we just need to be aware of as a developer. Whenever we're using a dangerously set inner HTML property, it's really important that we integrate these mitigation practices into our workflow. So again, you can validate content provided right there. You can practice defense in depth, making sure that user-provided content is clean on the client, on the server, on the client again, before showing it to the user. But you can also leverage tools such as ESLint or DOM Purify. So DOM Purify is a library that'll actually look at content provided to it, and it'll auto-escape things like script tags or button tags that users provide. This is really similar to what we saw in the first cross-site scripting attempt here, where React converted that script tag we provided it to a string. There's an HTML sanitizer API as well that's experimental that'll do essentially the same thing. If you're using ESLint in your workflow, there's this really handy no sanitizer with danger rule. What this rule does is it makes sure that any value provided to dangerously set inner HTML is passed through a sanitizer such as DOM Purify or HTML sanitizer API. If it's not, this will throw an error for you. Again, remember, never trust user input, always verify it. All right, so that concludes the demo portion of my attack. Demo portion of my presentation. We saw some successful attempts at cross-site scripting attacks, but we also saw some things React's doing today and will do in the future to help us prevent cross-site scripting attacks. If you're interested in trying to recreate these attacks, you can go ahead and clone this repo, the Syneva Runyan into the danger zone repo. It'll show you that fake social media profile, and you can go ahead and write some scripts, save it in the profile, and try to get your code to execute on the web page. It's worth mentioning that, again, this was not an all-encompassing presentation. There are other vulnerabilities, cross-site scripting and otherwise, that can be used to exploit React applications and any other application on the web. If you're interested in learning more, OWASP publishes a list of top 10 vulnerabilities that exist. You should also make sure just to practice basic mitigation practices in your workflow. You can do simple things like just keep your dependencies up to date. So leaving you with a final thought, make sure you're looking out for danger zones in your application. Whenever you do spot a vulnerability, make sure you're never trusting user input and you're always verifying what is providing you.